In this lecture, we'll be covering, continuing our coverage on slightly soluble compounds, the equilibria of those. And we'll also be talking a little bit about complex ions. And complex ions are metal ions typically that are surrounded and coordinated by other molecules. We'll just briefly touch on these in this class, in this quarter, but you'll see more of these when you take chemistry of the elements in the spring. And this will be our last lecture on equilibria systems. So specifically, we're going to be covering section 3 and 4 of chapter 19 today. Just to remind ourselves what the solubility guidelines are, I'm not going to go through these all again. We did that last lecture, but the more times you see these, I think the more you kind of sinks in. To be honest, like I don't really have these memorized even to this day, but you know, it helps every time you look at these. So it turns out, last time we talked about certain ionic compounds that we would consider insoluble, but they're actually, these insoluble compounds do dissolve slightly in aqueous solutions. So they're slightly soluble is probably a better, more accurate term for them. Well, it turns out that pH will have an effect on the solubility of some of these. Okay, so changes in the pH that affect the solubility of these very slightly soluble ionic compounds. What are they? Well, if you have the addition of an acid, that will increase the solubility of a salt that contains the anion of a weak acid. So here, if we look at an example, calcium carbonate, that's a slightly soluble compound. If you go back to the solubility rules, you'll see that carbonate combined with calcium makes an insoluble compound. Right? And the anion that it has is carbonate, and that is an anion of a weak acid. So if you add a proton or two to that, you'd get a weak acid, carbonic acid. So if you added acid to this solution, right, that acid's going to react. There might not be very many of these ions in solution, right, because this is only slightly soluble, but those that are in solution are going to react with that acid, that strong acid, and form the weak acid, right? And once that's formed, it doesn't really dissociate very much, right? But it is soluble. Right? And what that does, there's another step down here as well, right? Because this can add another proton, okay, and then become carbonic acid, which then is in equilibrium with a CO2 gas. Don't really need to know that part. But what you can think of is by creating this HCO3 minus, you're pulling carbonate ions out of solution, and then you're going to shift this equilibrium and draw it more to the right. Okay, so that's going to increase the solubility of your calcium carbonate. And this figure in the book just shows that when you're dissolving a carbonate material in an acid, you see these bubbles being formed. Those bubbles are this CO2 gas that's being given off. And so that's just an illustration of that. Okay, so let's try a practice problem with this concept. Write balance equations to explain whether the addition of acid from a strong acid would affect the solubility of each ionic compound. So we have lead to bromide, copper to hydroxide, and iron sulfide. Okay, so that first one was lead bromide. So first, it's lead 2 bromide, so we need 2 bromide anions to balance that. Okay, so we need to write the solubility reaction. Right, and this is a solid. Let's not forget that. and 2 Br minus. Okay, so that would be our solubility reaction. So when we add a strong acid, right, you could say H3O plus, or I just like saying H plus, easier. Right, we add that, again, it's aqueous. It's going to react with the anion, if it will react with anything, it'd be the anion. Right, so that would make HBr. Well, HBr is a strong acid. So when that is in solution, that's a strong acid. So when that's in solution, it's completely dissociated. So you're not, by adding acid to this, you're not going to be pulling away bromide ions out of solution. So this one's going to have no reaction, no effect. So let's look at B, copper hydroxide, copper OH2. That's solid. Copper 2 plus ions and OH minus. Okay. So if you look at OH minus now, if that reacted with H plus, what would that produce? That would produce water. Okay. So water actually is a weak acid itself. So this is an example of one of those cases where adding an acid to this will remove those hydroxide anions and the solubility will increase, the solubility of the copper hydroxide. Okay. And that, again, it's because that acid, the H plus, is going to react with those hydroxides and form water. Okay. And once water is formed, it doesn't dissociate very much, right? It's kind of like a weak acid, so it doesn't dissociate. And you will effectively pull out those OH minuses and get them out of solution. Okay, finally, we have iron sulfide, FeS. Again, that's a solid. That makes iron 2 plus ions plus S2 minus anions. Right, so if an acid now, if you add an acid, it's going to react with the S plus anions and make HS minus. And this turns out to be, yes, it is a weak acid. Okay, and that's the next step. You'd actually have a second step here. 2 protons could react, and you'd get H2S. Okay. So those are weak acids. So solubility would increase. Okay. The book gives this example too. It's of limestone. Limestone's mostly calcium carbonate, and it gives the KSP value there. Right, so groundwater that's rich in CO2 trickles over calcium carbonate, and that causes some of this to dissolve, right? Because you have the CO2 there, it shifts the equilibrium, and you're going to dissolve some more of the carbonate out. Then water containing that anion drips from the ceiling, where the air has a lower partial pressure than the soil and a lower pressure in general. And what that causes is carbon dioxide to come out of solution. That shifts the equilibrium back to the calcium carbonate form, and it solidifies again. And that's what forms these stalagmites and stalactites. So the exact equilibria is shown here. it's kind of complex because you have the equilibria of the carbon dioxide and gas in aqueous. Then the aqueous carbon dioxide's in equilibria with H2O to form an acid and H3O CO3 minus. Okay, and then that is affecting the equilibria of your calcium carbonate, right? Because when CO2 is aqueous, you can form these HCO3 minus anions as well. It can help dissolve this, right? But once you lose that CO2 out to the air, then it shifts that equilibrium back. Okay, not a super important reaction or equilibria to remember, just an example of how stuff we're going over in class, how it kind of affects real world environmental situations. One of the more important things to do when we talk about solubility is, much like just in general equilibria, when we're comparing QC to KC and deciding which direction a reaction would go, we can also compare QSP to KSP to determine if a precipitate is going to form. And so that is, in this part of the book, this material, this might be one of the more important things to be able to do. Definitely going to show up on an exam. Okay. So a saturated solution of a slightly soluble compound, the QSP equals the KSP. Okay. When the two solutions containing ions of slightly soluble salts are mixed, right, if QSP equals KSP, the solution is saturated and no change is going to occur. If QSP is bigger than KSP, what does that mean? QSP, remember those expressions are the products. So if the products are higher in concentration, then they should be at equilibrium, right? This is their solubility, right? And if QSP is higher than that, that means they're too saturated, right? And they're going to, they're oversaturated. So that means they're going to precipitate until they reach that saturation point, until QSP equals KSP. And if QSP is lower than KSP, no precipitate will form because the solution is undersaturated. So here is kind of a difference between QC, KC, and QSP and KSP. If QC was lower than KSP, the reaction would just run in a different direction. Here we don't get any precipitation reaction at all. It just doesn't happen. Okay. And again, this is a reminder of our general equilibria expressions and the directions that they go. So let's try a practice problem with this concept. A common laboratory method for preparing precipitate is to mix solutions that containing the component ions. Does a precipitate form when 0.1 liters of 0.3 molar calcium nitrate is mixed with 0.2 liters of 0.06 molars sodium fluoride? So what precipitate's going to be formed? Well, sodium's always going to be soluble, and so is nitrate. So it's going to be the precipitate's going to involve calcium and fluoride. So calcium fluoride is what we're going to be precipitating here. So how do we go about a problem like this? Well, first we had to determine which ions are going to mix to make the slightly soluble or insoluble compound, right? And so that would be calcium fluoride. That's what we're really concerned with. That's what we're going to have as a precipitate. And to really answer this, we're going to need to know the KSP. So the KSP value for this, which I don't believe was mentioned in the problem, but you can look up. It's not mentioned there, but you can look this up in the book. 3.2 times 10 to the minus 11th. Right, you could probably look that up online too, although it might be slightly different than the book value. So what would our reaction be? Our reaction would be calcium fluoride solid it's in equilibrium with calcium 2 plus aqueous plus 2F minus aqueous. So that's our equilibrium solubility. And then we can write an expression for KSP based on that. It's going to be the calcium 2 plus concentration times the F minus concentration squared. Right, so we have the KSP, we have a expression for KSP. Now we need to determine if the solutions we're mixing, the actual QSP for them, and I should mention, right, that's the same formula we're going to use to calculate QSP. So we're going to use that to calculate a QSP and compare that to our KSP value that we looked up. So to do this, we need to determine the moles of calcium and the moles of fluoride that we have, and then the final volume that we're going to get the final concentrations of each. So if we look at calcium first, we had 0.1 liters of 0.3 moles per liter. So we had 0.03 moles. Right. So the concentration, whoops, sorry about that. The concentration of calcium is going to be 0.03 liters, or excuse me, moles, divided by the final volume. So we had 0.1 liters of calcium, 0.2 liters of the sodium fluoride. So that'd give us a total of 0.3 liters in volume at the end after we mix these. So our final concentration would be 0.1 molar. Okay, we do the same thing for fluoride. Here we had 0.2 liters of 0.06 molar, which gives us 0.012 moles. So 0.012 moles divided by 0.3 liters, right? Same final volume, which is 0.04 molar. Okay, now we need to plug this into our expression for QSP. Okay, it's calcium 2 plus times fluoride minus squared. So calcium is 0.1 molar. Fluoride is, having trouble here with the controls, 0.04 molar, but that is squared. So when you do that multiplication, you should get 1.6 times 10 to the minus 4. And again, order of operations matter here, so just be aware of that. You need to square the 0.04 and then multiply it by 0.1, and not multiply 0.1 by 0.04 and then square it. Okay. So here we have a QSP of 10 to the minus 4. KSP is 10 to the minus 11th, so QSP is bigger than KSP. All right, what does that mean? That means your products in solution are greater than they should be, so that means a precipitate is going to form. The reaction is going to go the other direction. Okay, precipitate will form. And it forms until QSP equals KSP. Okay, let's try another problem based on this relationship. Okay, we have 4 molecular scenes representing solutions of silver, which is gray, and carbonate, which is black, black and red. So you have silver, carbonate, and silver carbonate in solution, in a mixture. Okay, which scene best represents the solution in equilibrium with the solid? And which, if any, other scenes will additional solid silver carbonate form? And explain how, if at all, addition of a small volume of concentrated strong acid affects the concentration of silver plus in solution in scene 4 and the mass of solid present. So first, let's look at the part A. So part A is asking which scene best represents the solution in equilibrium with the solid. And what is our reaction for this? Well, our reaction is Ag2CO3 and that's a solid. Pen is acting up today. Okay. So that's our equilibrium. So what does that mean? We need 2 silver ions and 1 carbonate ion. So if we look, so we need that ratio of 2 silvers to 1 carbonate. So if you look and count that up, scene 3 would actually be a good representation of that. There's actually 4 silvers and 2 carbonates, but that would be the same ratio. So scene 3 is the representation of that. Okay, so for part B, in which, if any, other scenes will additional solid silver carbonate form? Right, if we look at scene 3, and assume QSP equals KSP for it, right? What is, how do we calculate that? It would be silver plus squared times carbonate. So we have 4 of them squared times 2 for the carbonate. So that'd be 32. Right, and now if we looked at scenes 1, 2, and 4, we can calculate QSPs. Scene 1, we have 2 silver pluses, so 2 squared times 4 carbonates, so that's 16. So here QSP is less than KSP. QSP equals 3 squared times 3 for scene 2, right? There's 3 silver pluses, 3 carbonates, so that equals 27. That is still less than KSP. So nothing's going to happen. And then finally, scene 4, QSP equals 3 squared times 4, which is 36. So QSP in this case is greater than KSP. So you're going to get a precipitate here. So precipitate will form in scene 4. Okay, finally, part C. If we add an addition of small concentrated acid to that scene 4, how will that affect the silver plus concentration? and the mass of solid present. Okay, so what's going to happen here? If we add the acid's not going to react with silver plus, right? It's going to react with the anion, so the carbonate. That would form HCO3 minus, and then you could have another H plus that would react with that and form H2CO3. Right, so what that does is it's going to pull carbonate out of solution, right? And when it pulls the carbonate out of solution, it's shifting that equilibrium to the right side. So it's going to make this more soluble, so your Ag plus concentration will go up, and the amount of solid you have will go down. So Ag plus in that scene would go up, that concentration, and your solid precipitate, or your solid silver carbonate, that's going to decrease. You can use this principle to selectively precipitate out certain ions in a mixture. And how you do this is a precipitating ion is added to the solution until the QSP of the more soluble compound is almost equal to its KSP. Okay, so its QSP of the more soluble compound will be close to its KSP, so close to saturation. So it still will not have precipitated out yet. But what that does is the less soluble component will be precipitated out as much as possible without losing the component in the solution that you're interested in, that you're trying to separate. So let's try a practice with this concept, and this is a pretty complex idea, but let's go through a problem like this. Okay, you have a solution that consists of 2.2 molar magnesium chloride and 0.1 molar copper chloride. So basically what you have are magnesium and copper ions in solution. These are strong electrolytes. They'll be fully dissolved, right? They're chlorides. What we have to do now is calculate the amount of base that we need to separate these metal ions. Okay, we want to separate the magnesium and the copper from each other. Okay, and by adding the OH, the hydroxide anions, they're going to form magnesium hydroxide and copper hydroxide, both of which are insoluble, or only slightly soluble. And you'll see that they have different KSP values. Right, magnesium is 6.3 times 10 to the minus 10. Copper hydroxide is 2.2 times 10 to the minus 20. So they're a great deal different in solubility. So magnesium is going to be more soluble. Copper will be less soluble. Okay. So how do we go through a problem like this? Well, first we need to write out our equilibria. And magnesium chloride and copper chloride, right? They're just going to dissociate in solution. We know we have 0.2 molar and 0.1 molar of each of these, right, stated in the problem. Okay, so we know the concentrations of these ions, the magnesium and the copper. We're told that magnesium hydroxide has a KSP of 6.3 times 10 to the minus 10, and copper hydroxide has a KSP of 2.2 times 10 to the minus 20. And we know that they're their solubilities in the hydroxide form anyways are going to be the same, right? We're going to have magnesium OH. That's going to be in equilibrium with Mg2 plus 2 OH minus. Right, so these are solids, and on this side we have aqueous. And copper is just going to follow that same pattern. So we can write our expressions for KSP or QSP. They'll both look very similar. The metal ion concentration multiplied by the OH minus concentration squared. Okay, so that'd be magnesium and copper, it's going to be the same, except now you're replacing that with copper 2 plus concentration. Okay, so we can solve for OH minus in both, that concentration. So when we do that, we find it's going to be the square root of our KSP value divided by magnesium concentration. And when we plug in those values for KSP and for magnesium 2 plus concentration, right, so we would get KSP for the magnesium hydroxide 6.3 times 10 to the minus 10. The concentration of Mg2 plus is 0.2 molar. Take the ratio of those and do the square root, you get 5.6 times 10 to the minus 5. And when we do that for copper, we get 4.7 times 10 to the minus 10. So what are those? Those are the maximum OH minus concentrations that you can have that will not precipitate out any of the metals in question. So we could add 5.6 times 10 to the minus 5 molar OH minus to this solution and not have any magnesium precipitate out. And likewise, for copper, we can only add 4.7 times 10 to the minus 10 molar, so much, much less OH minus that we could add until we precipitate some copper out. So copper is going to precipitate first. So if you added OH minus to this point, you're going to precipitate out the copper. And we can rearrange that expression, the KSP expression, to solve for a copper concentration. Sorry, OH minus squared. And now we're using the KSP for copper because that's the least soluble that we're trying to precipitate out. And now we divide it by our OH minus concentration that we calculated, where none we can add up to, so no magnesium precipitates out. We add that in here. And this will tell us how much copper we can precipitate out without losing any magnesium. It turns out this is 7 times 10 to the minus 12 molar. Right, so that's how much copper would be left. So we're going from the start was 0.1 molar. And by adding that OH minus, we're going to drop it to 7 times 10 to the minus 12 molar. So essentially, That's 7 picomolar. So essentially that's, no copper there anymore, and we haven't really lost any magnesium, okay? There are certain aspects to this part of the material in the book that line up with environmental chemistry. So if you're interested in environmental chemistry, there's a lot of applications to the equilibria of insoluble compounds. And one of those is acid rain. A pH affects the solubility of many of these insoluble ionic compounds. So acid rain can really affect many aspects of the environment, and this figure just shows that. Okay, you have gaseous compounds like SO2 and certain nitrogen oxides that released by burning, one of the ways they're released by burning coal. You also get some NO emissions released from burning car fuels. Okay. They can be oxidized by either oxygen in the air, hydrogen peroxide, ozone, or superoxide radical, and they produce things like SO3 and NO2, which then can react with water, and this is what makes acid rain. You get the H2SO4, sulfuric acid, and nitric acid that's dissolved in rain and snow, and then that rain comes down, it washes over the soil and the rocks, and that can affect solubilities of certain minerals, and then you can get that leaching out into water supplies, which may or may not be a good thing. The last part of chapter 19 that we're going to cover, it deals with equilibria and formation of what they call complex ions. So a complex ion consists of a central metal ion, and it's covalently bonded to 2 or more anions or molecules called ligands. Okay, and so this is an important point, that the positively charged metal ion is covalently bound, and it's bound. We usually think of positively charged metals being bonded to negatively charged anions, but it can also be bonded to neutral molecules, things like NH3 or H2O that don't have a real full charge to them. They're just polar molecules, can form these bonds to the metal ions as well. And again, they're called ligands. Some people pronounce this as ligands as well. I don't actually know which one is technically correct, but I like ligands. We look at one of these. We have a generic metal M, and you can exchange these ligands in solution. So let's say we have our metal that's coordinated with 4 water molecules to start. If we add some ammonia into this solution, what can happen is now these ammonia can replace water as one of the ligands for this metal. And if you do this enough, you can replace all of them. And when you go into lab, next quarter, you'll be doing experiments like this in the lab class. And this is kind of what you would consider inorganic chemistry. Some of these complex metals can have what's known as amphoteric behavior. And that is, they can act like a base or an acid. So you add solid aluminum hydroxide, you can treat it with acid or with base, and it dissolves as a result of the formation of soluble complex ions. So here we have the solid aluminum hydroxide, and it's coordinated actually with 3 water molecules and 3 OH molecules, OH minus. Okay, and it's in a solid. Okay, you can just put this in solution, and it's slightly soluble. but then you add acid or base to it, and it pulls it out of the solid into solution. It solubilizes it. So what's going on? So if you add acid to this, what's happening? What you're doing here is this acid is going to be reacting with the OH minus anions that are in this solid, and then pulling that aluminum out, and it's going to be coordinated with 6 waters now around that metal. Okay, so that solubilizes it. When you add OH minus to this, what you get is you actually get an OH minus that coordinates the aluminum. So now we have 4 OH minuses and only 2 H2Os, and that again can solubilize it. Okay, not as obvious as to why. You're just adding more charges there, I guess, to balance the water charges. But it's more obvious as to a good reason why you would add acid to solubilize that. Okay, so let's try finally some practice questions with complex metal ions. And these, pardon the pun, but these questions can get very complex. Okay. So this one, we have an industrial chemist is converting zinc that's coordinated by 4 water molecules. So it's a zinc 2+, and it has 4 water molecules around it, to the more stable zinc ammonium 4. So it's coordinated now by 4 NH3 molecules. And I guess I shouldn't say ammonia, it's ammonium. And again, that zinc hasn't changed its oxidation state, it's still +2. Okay, and they're doing this by mixing 50 liters of 0.002 molar zinc tetra water and 25 liters of 0.15 molar NH3. Okay, so they have this zinc tetra water, and they're adding the ammonia to it. What is the final zinc concentration of zinc tetra water at equilibrium? And they give this expression here, Kf of zinc NH3 is 7.8 times 10 to the 8. So what is that? Kf is a formation constant. Okay, so you can write this reaction that's occurring out down here, right? We have our soluble zinc H2O4. You're adding NH3 to that, and you're forming your complex ion zinc NH3 and the formation constant for this. Usually you would do products over reactants, and it's the same way, right, for Kf, right? Your product is that complex ion, and your reactants are what you started with, the solutions you started with. Okay, so we write that the same way, but now this is an equilibrium of how much of this complex ion are we forming. Okay, so let's first remind ourselves of that reaction. We have zinc H2O4, 2+, in solution. We're adding 4NH3, aqueous in solution. What we get out is that zinc NH3, 4, and 4H2O. So we can write our expression for Kf. And we know what that value is, right? They gave it to us, 7.8 times 10 to the 8. And write that expression for Kf, which is, we do that the same way we would write an expression for KSP or Kc, right? They're always products over reactants. Whoops, that's H2O, not OH. times concentration of NH3 to the 4th power. Okay, so that's our expression. Next is to set up our reaction table. So initial, change, and equilibrium concentrations here. Okay, so what do we get at our initial concentration? Well, this is where it gets a little bit challenging because they're giving us a volume and a concentration for each of the component mixtures. Okay, so it might be very tempting to say, okay, the initial concentration of our zinc tetra water is 0.002 molar. But then you mix it with 25 liters of the NH3 solution. So you have to take that into account. Right, so to do that, we're going to have to say, calculate the number of moles we have. So that'd be 50 liters times 0.002 molar. And then we would divide that by our new volume. So our new volume, we started with 50 liters and we added 25 liters of that. So 50 plus 25 would be 75 liters. Right, so when you do that, you get something like 0.00133 molar for our zinc tetra water. Our NH3 now is 25 liters times 0.15 molar divided by 75 liters, which is 0.05 molar. And then we're not starting with any of, I guess that should be 0, and we don't care about water. So we're not starting with any of that complex ion. So how is this going to react? Well, we're going to react in the direction of the formation of, we're assuming we're going to react in that forward direction to the right because we don't have any of that complex ion to start. So what we do here is the solution that's in the lowest amount is what we're going to use the most of. So in this case, our change, we'd use all of this zinc tetra water. Right? And so you might be tempted to write in, 0.00133 here, but there's a 4-to-1 ratio of NH3 that's being used. So we'd have to multiply that by 4. When you do that, it's 0.0052. And produced is going to be equal molar amount to what we started with in our zinc tetra water. Okay. So at equilibrium, we can set these values equal. We could say 0 there, essentially. Although we don't really know that because we don't know, we need to factor in this equilibrium, this formation constant. So let's keep that x here. If we subtract 0.05 minus 0.0052, we get approximately 4.5 times 10 to the minus 2. And then we know we're going to produce about 1.3 times 10 to the minus 3 molar of that final compound. Right, so now we need to solve for x. Whoops, not minus 8, it's plus 8, because it's a formation constant now. So if we had 1.3 times 10 to the minus 3 divided by x times 4.5 times 10 to the minus 2 to the fourth power, right? When we solve for x, and x equals our starting concentration of zinc tetrawater, it'll be something like 4.1 times 10 to the minus 7 molar. So we've used up quite a bit of that. We've gone from 1.3 times 10 to the minus 3 to 4.1 times 10 to the minus 7. Another way you might be asked to solve this problem is to calculate a final concentration of your product. Okay, the final problem dealing with equilibria here, and we're just not going to focus on the second part of this, part B. That gets really complex, too complex for this class. But let's look at part A, and this is actually a pretty simple question. Okay, in black and white film developing, excess silver bromide is removed from the film negative with hypo, which is an aqueous solution of sodium thiosulfate, which causes the formation of the complex ion silver thiosulfate. Calculate the solubility of AgBr in water. So we won't really focus on how complex this can get. Let's just calculate that solubility in water. And first, we would need to write our reaction. So silver bromide is the slightly soluble compound. It dissolves into Ag plus aqueous plus Br minus aqueous. Our KSP we can write for this is that expression, silver plus concentration times Br minus concentration. Very easy. We look that value up. It is 5 times 10 to the minus 13. Okay. Well, at equilibrium, right, we don't know how much we have starting with this, but let's just call it Y amount. Don't have any of those before. Then the change we would have is that would lose some of that solid. It would become solubilized, and we gain the same amount of each of those ions. So at equilibrium, this would be Y minus X. Both of these would be X. Okay, so we don't really know anything about Y, so we can't really speak to how much we're starting with in that, but we know how much is going to come into solution of both the ions based on the KSP value. So we would set this KSP value, it's just going to be X times X with those, what we've determined our equilibrium concentration variable is, so X squared equals 5 times 10 to the 13, negative 13. Take the square root of both sides. So what we would get is X equals 7.07 times 10 to the minus 7 molar. So that would be the solubility of AgBr in water. That's how much silver and bromide ions we would get when we try to dissolve this in water. Okay. So that is all we have for this quarter in the chapters dealing with equilibria. The next part of this class is going to deal with kinetics in chapter 16. So the next 3 lectures are going to be dealing with that material, and then it'll be the end of the quarter. So we're getting close. We're getting close to the end.